Alright, it's time to shift gears and start looking at differential equations. We'll still have a little bit of linear algebra in here, but mostly differential equations. I think I've mentioned these before. A differential equation is an equation in x, y, and derivatives of y. So first derivative, second derivative. I guess we usually do double prime for second derivative. And then maybe after that we can use numbers in parentheses. A solution to a differential equation is an equation in x and y with no derivatives in it. If we say solve a differential equation, that means find all solutions. So for example, let's check that y equals e to the negative 2x and y equals 3 e to the 3x are solutions of the differential equation y double prime minus y prime minus 6y equals 0. So I'm giving you the solutions for now. And if you're wondering, how do we find the solutions? That we're going to do later. So for now, let's just check that there's solutions. So for y equals e to the negative 2x, we have y prime equals negative 2 e to the negative 2x, and y double prime equals 4 e to the negative 2x. So if we take the second derivative, 4 e to the negative 2x, minus the first derivative, minus negative 2 e to the negative 2x, minus 6 times the function, minus 6 e to the negative 2x. What does that give us? We've got 6 e to the negative 2x minus 6 e to the 2x. So since this satisfies the equation, this linear combination of the function and its derivatives equals 0, then y equals e to the negative 2x is a solution. For y equals e to the 3x, we have, let's see, so y prime equals 3 e to the 3x, and y double prime equals 9 e to the 3x. So now if we plug these into the left-hand side, I wonder if we get 0. So the second derivative, y double prime is 9 e to the 3x minus the first derivative, minus 3e to the 3x minus 6 times the function minus 6 times e to the 3x equals, so 9e to the 3x minus 9e to the 3x is 0. And y equals e to the 3x is a solution. No derivatives here, no derivatives there. Those are the solutions. We call the differential equation nth order linear. If it has the form nth derivative of y plus some function of x n minus first derivative of y, etc., up to some function of x y equals some function of x on the right hand side. Linear because we're adding sort of a linear combination of the derivatives of y. Our scalars are functions of x. Nth order because the nth derivative is the highest derivative we see. We call this equation homogeneous if the right-hand side equals 0. So if we have this linear combination of derivatives equals 0, and we say it has constant coefficients, if each of these functions ai of x is just a constant. For all I. And we're mostly going to be interested in this course in the case where these coefficients of the derivatives are just constants. Oops, that's a little bit off the screen. We will focus mostly on constant coefficients. Now, I think when we did vector spaces, one of our examples was solutions to a homogeneous linear differential equation form a vector space. So recall that solutions to an nth order linear differential equation form a vector space. Oops, it has to be homogeneous. We have to have equals 0 on the right hand side. So solutions to a homogeneous nth order linear differential equation form a vector space. While I'm at it, I'll say solutions to a non-homogeneous, so f of x on the right hand side is not the 0 function. Solutions to a non-homogeneous differential equation do not form a vector space. Right. But solutions to a homogeneous nth order linear differential equation do form a vector space. And in fact, this vector space has dimension n, the highest derivative that we see. So we should be able to find a basis that consists of n functions. So if we find n linearly independent solutions then they form a basis for this space of all solutions to the homogeneous differential equation. Now recall that we used the Wronskian to decide if functions are linearly independent or not. So the Wronskian helps us decide if functions are linearly independent. And actually, if we have functions that are all solutions of the same differential equation, then the Wronskian helps us even more than it did before deciding if randomly selected functions are linearly independent. So if y1, y2, etc. up to yn are solutions of a linear an nth order linear differential equation, I think it has to be homogeneous. An nth order linear homogeneous differential equation then there's two cases. Either the Wronskian of yn through yn equals 0 always. So by always I mean for all x. And y1 through yn are linearly dependent. Or, so this is the first possibility. The second possibility is that the Wronskian of these solutions is non-zero always. Again, for all x I mean by always. And y1 through yn are linearly independent. So we can test y1 through yn for linear dependence or independence. By evaluating the Wronskian at any value of x we like. So there's no danger of choosing the wrong x, because it's either going to be 0 for all x or it's going to be non-zero for all x. So any value of x we choose is going to be a good enough test. So for example, let's look at the two solutions to the differential equation that we had before. So we had y equals e to the negative 2x and y equals e to the 3x. These are solutions of y double prime minus y prime minus 6y equals 0. A second order homogeneous linear differential equation, which happens to have constant coefficients. Now the Wronskian of e to the negative 2x, e to the 3x is the determinant of the matrix we get by taking these functions in the first row and their derivatives in the second row. So negative 2e to the negative 2x and 3e to the 3x. And that equals, see, 3 e to the 3x times e to the negative 2x is, let's see, when we multiply exponentials, we add their exponents. So that's 3e to the x minus negative 2 e to the negative 2x times e to the 3x. So again, that's e to the 3x minus 2x is x. So I guess we have 5 e to the x. And no matter what value we plug in for x here, e to that value is not 0. So this is never 0. So that means that e to the negative 2x and e to the 3x are linearly independent and form a basis This is the basis of the solution space of y double prime minus y prime minus 6y equals 0. In other words, all solutions are the linear combinations of these two functions. c1 e to the negative 2x plus c2 e to the 3x, where c1 and c2 are any real numbers. All right, this is a homogeneous differential equation because the right-hand side is 0. Now let's look at non-homogeneous differential equations. To solve a non-homogeneous, that is, the right-hand side is not just 0. A non-homogeneous nth order linear differential equation so let me write it out. Let's say nth derivative of y plus a1 of x n minus first derivative of y plus a2 of x n minus second derivative of y plus up to anx y equals f of x. We write it, and let me call this equation NH. For non-homogeneous. We write it, and the related homogeneous differential equation I'll call the homogeneous one H. Now this is going to be the exact same thing, except I'll write equals 0 on the right hand side. So nth derivative plus a1 of x times n minus first derivative, etc., up to anx y equals 0. So this is the differential equation we want to solve, and this homogeneous version is going to help us. So then we'll find any one particular solution of the non-homogeneous equation. Call that yp of the non-homogeneous. We'll find all solutions c1, y1 plus, etc., c n, y n. We'll basically find a basis and then say all linear combinations of those basis elements of the solution space of H are all solutions. So find all solutions of the homogeneous linear differential equation. Then the set of all solutions of the non-homogeneous differential equation. Is yp plus all possible solutions of the homogeneous differential equation. All possible linear combinations of these basis elements. So again, to get all solutions of the non-homogeneous equation, we just need to find one solution of it. And that solution plus all solutions of the homogeneous differential equation are going to give us all solutions of the non-homogeneous differential equation. How we find that one solution is going to come up in a later video. And as I said, how we find all solutions of the homogeneous differential equation is going to come up in a later video. But let's look at the reason why this should be true. Why is it the case that to find all solutions of the non-homogeneous system, it suffices to find just one, and then we can add to that one all solutions of the homogeneous system of the homogeneous differential equation, and that should give us all solutions of the non-homogeneous.